So my name is Ryan Quinn, and today I'll be presenting this crazy long title, which is just a joking way of saying that we're going to talk about Constexpr everything today, and a practical application of how to quite literally write everything in a Constexpr. Okay, that doesn't work. So before we get into exactly the details of this, I think it probably makes sense for us to first discuss exactly what is a Constexpr and what is Constexpr everything. So a Constexpr, if you look at this little code example here, is essentially labeling your function as a Constexpr. What it basically means is that you are now capable of executing this function at compile time instead of runtime. You can do this also with variable declarations and all sorts of other things, but generally speaking, the best example is usually a simple function. What we mean by Constexpr everything is quite literally everything is labeled with Constexpr. And it's not enough to just say that we add Constexpr to the definition, but we also want to ensure that it can be compiled as a Constexpr. So not all Constexpr functions that are labeled Constexpr will actually compile in a Constexpr. So the short of it is I write a function, I can run it at compile time and not at runtime, or I can use it at runtime too, but the point is compile time.
So is the
Yeah, there's actually a number of examples, but yeah, I mean, Constexpr was added in C++11, but yeah, there are a fair number of different things that you can do. For example, you could actually run code that's not labeled as Constexpr from a Constexpr, and there's actually a way to do that from a unit test to actually prove or to show an error message when you run a Constexpr. Which if I have time, I can go into that. So again, why would we do Constexpr for everything? And the first two are the things that we tend to think about the most. It allows us to be more flexible with our code, and usually the thing that we care about the most is optimizations. Right? We can do a lot of the code that we need to at compile time instead of runtime, and so that reduces the amount of work that's done at runtime. But there's a third thing that's actually quite interesting about Constexpr that a lot of people don't know, unless you started to write this code yourself, and that is you're not allowed to execute any forms of undefined behavior from a Constexpr. And the way this works is the compiler actually executes your code at compile time, and if it runs into something that it defines as undefined, it will throw an error and say you can't do that. And this is a really intriguing aspect of Constexpr that we're going to talk quite heavily about in this presentation. So you might be asking, what is undefined behavior? So undefined behavior is quite literally just anything that the program executes that's not defined by the specification, in which case the code is allowed to do whatever it wants. So you might, for example, add 1 to max, and you might get any return value between min and max as a result, because if that's a signed integer, that would be undefined. I can read the value outside the bounds of an array, or I could dereference a null variable. These don't always necessarily lead to segmentation faults, right? You might actually put some weird random value inside of your pointer and dereference it. It might work, and you wouldn't know about it until later. All it basically is just saying is I'm doing something that's undefined by the specification. So then, why do we have undefined behavior? Well, I just gave you a whole bunch of reasons why undefined behavior is horrible, right? But in reality, undefined behavior is a good thing. It allows us to optimize our code. And I don't want to go into all the examples of how that's done. If you're interested in exactly how that works, Chandler gave a fantastic presentation on this topic in 2016. I was actually there for that. It was really good. So if you want to know more about why undefined behavior exists and why it's a good thing, so long as we never invoke it, of course, please go check out this presentation. It's amazing. So how does all this relate to this talk? Well, there are many different attributes that we can give a program. We can define a program as whether or not it's valid or invalid, whether it's defined or undefined, ill-formed, unspecified. We can make, we can try to determine, is it performant for our particular application? Is it deterministic? If you are watching a lot of the conversations around exceptions, this is a really big problem right now with exceptions in C++ because they're non-deterministic. So in this presentation, I'd like to focus just on whether it's invalid or undefined. So a valid program is a program in which for any input, we get an output that's known and expected. So here I've shown an AND gate, right? It's a very simple example of a program, but I give it whatever inputs I give it, I get my expected output. That would be a valid AND gate. A defined program, in this definition, we don't care about what the output is, right? We're not evaluating the output. We're evaluating how the program got to that output. The output could be total garbage, but did it, given any input, come to the output that it came to by executing undefined behavior or not? So a well-defined program, no matter what inputs you provide, and for all inputs, will always come to whatever output it came to without executing undefined behavior. And so obviously we have a problem. If the idea behind these two definitions that came up with is all inputs, I can either determine if it's valid or I can determine if it's defined. Well, the reality is I can't test all inputs, right? It's impossible. You can take a simple function with a 64-bit integer and you can't test every single possible value. You can't write a program that would do it. And nonetheless, if you start adding more and more inputs. So what we try to do is we break down our testing into different types of testing. We have unit testing and integration testing and system testing. And then we have different schemes on how we go about doing this testing. For example, with unit testing, we're not going to test from int min to int max. We're going to test certain boundary conditions. And so really, a unit test is just a fancy way of saying I'm going to test some code at the subcomponent level. So instead of testing the entire program, I'm going to break it down into its subcomponents and then test each subcomponent in isolation. The problem with unit testing is that it won't tell me if I have a valid program. In this example here, I have different combinations of different subcomponents. I have some AND gates and some OR gates. And I've unit tested the OR gate and the AND gate to prove that both of those do exactly what they're supposed to. Given all inputs to the OR or AND gate, I get the expected output. But I can combine these subcomponents in any order and any combination I want to produce whatever output I want for the final program. So I can unit test all of my subcomponents all day long, and I'm never going to know if I have a valid program. To determine if I have a valid program, I have to give the program all of its inputs and verify that the program itself outputs everything as expected. But I can use this to determine if my program's defined. If I were to produce a unit test for each subcomponent and determine that every subcomponent, given all inputs, never executes undefined behavior, then I can combine all of my various different subcomponents in any order I want, and it too will never execute undefined behavior. Again, assuming that I'm able to test all inputs. In practice, we can't do that. So the goal is to try and get as close to that as possible, right? This is some fancy graph that basically shows as I add more and more and more tests, I get closer and closer to essentially not seeing any sort of ROI associated with adding more and more tests for my undefined behavior. So with all that background in place, let's talk about this sort of simple example. So I have a function at the top called foo, and it takes an input and verifies is it 42 or not, and returns true or false. From here, I have my sort of unit test, and it goes through the different success and failure cases. In reality, the only test I really need to worry about is whether it's 42 or not. But I could add a couple more, like some boundary conditions. Is it max or min, or that kind of thing. If I continue to add more failure cases, you will see that the ROI associated with every new case I add is pretty much 0. So for the most part, for this function, I've essentially determined, or I've sort of hit that sort of place where we want to be with respect to unit testing. The trick, when I write my unit test, is that the very last line is what we would normally do. We would run the test function, and we would check is it success or failure, and then return a success or failure code as a result. But the line right above it is how we do it at compile time. We run that unit test function from a static assert. That forces that entire function to run at compile time. So when I execute my unit test, or excuse me, when I compile this code, it will execute my unit test while I'm compiling it and actually tell me if it was success or failure. I can then run my unit test and, for example, hook that into like a code coverage tool or something like that, so I can then get some output as to how well my code was covered or whatever. There's a lot of other things that are super helpful if you do this at runtime as well. But the point is when you go to run it at runtime, you're already going to know if it passes or fails. That part's already been determined because it compiled. It wouldn't have compiled if it failed. So this is the basic structure for how you can write your unit tests such that they are all done at compile time. So let's do a quick demo, just so you can kind of see this in action. We good? Okay. All right, so here's that same example, right? So we have our foo function, and we can, see, what we're doing here. From here, I can, that's weird. There it goes. Yep. So from here, I can compile my example, and it compiles just fine. It tells me, hey, everything's passed because it compiled. Can then have some fun with some different examples of things that would generate undefined behavior. All right, so in this example, this is really horrible. You should never do any of this. Right? I'm taking the address of a temporary variable as my parameter, and then I'm trying to set it equal to 42, but then for whatever reason, I have no idea why I decided that if it happens to be 42 as the input, then I'm going to nullify that pointer, and bad things will happen. And when I execute this, you can see that I get a nice little output from the compiler saying I've dereferenced a null pointer. Now, if I didn't do this from compile time, this will compile, and I can execute this code and watch it segfault, right? So the fact that I ran this at compile time helped me determine, before I tried to run the code, that I've actually introduced undefined behavior into my program, simply by just executing my unit tests at compile time. Now, this is a really simple example. It's obviously pretty obvious that this was going to happen just by looking at the code. But from a really big program, when you're adding all sorts of code and the conditions can change and weird things can happen, this can save you a lot of time, because the code itself just told me while it's compiling that, hey, something bad has happened and it's going to happen when you go and try and run this. Versus, I compile it, I don't know something's going on, I then got to set up my test environment and get everything all and running just to find out 5 to 10 minutes later that I've made this mistake. So, and there's a whole bunch of different things that we can do here. This one's obvious, right? I dereferenced a null pointer. But what happens if I do a simple piece of code like this? Can anybody tell me what's wrong with this? Good job. I heard someone else say it too. So we can see here the compiler is like, hey, I'm trying to read from an uninitialized variable. Again, this would compile. I would run. Now this wouldn't generate a seg fault normally. This would actually produce some pretty wonky, weird behavior. It may actually work, right? It might be that 0 is on the stack, and this may have actually worked for quite a while. It may have also been that it wasn't, and something horrible happened. This may actually work for years and years and years until finally somebody decides to call this function in a different order, changes the values on the stack, and then bam, it breaks, right? But by running this in the const expression, I'm capable of detecting this right off the bat. And all I had to do was run my unit tests at compile time, and it was able to tell me that, hey, I've got a problem here. Good question. Yeah, if you use that too much, it will totally break this apart. Now, it can also be really helpful. So when we get to the end of this, once we get actually past this demo, I'm going to go into a real-world example where we built an entire microkernel capable of executing applications that's written entirely as a const expression. And there are a couple of places where we use that, specifically, for example, when we print stuff to the screen. There's nowhere to print, right? So we used that exact code to basically bypass that branch to say, okay, if I'm in a const expression, don't bother, and it won't execute that little piece of code. You can also do that, for example, for dealing with assembly code if you need to. But again, every single place you put that, the code that's in the other half of that branch is never going to be found by this. So, very good question. No. Yeah. So, so that was very good. So I spent some time hand picking some of these to make sure that I picked ones that showed some nice output from Clang to put it in the best light I could. The reality is there's a fair number of Clang scenarios where it just says this didn't compile as a const expression and has no idea why. It won't tell you. It doesn't tell you where, doesn't tell you what the issue was, it just says I couldn't compile. So I'm really hoping the compilers get better over time with that because this is fantastic, right? I mean, if they all produced this thing, I mean, it's not just telling me exactly what happened, it gave me a full backtrace, right? Which is awesome. And so it needs to do that for all of the const expression issues, and unfortunately it doesn't. So you caught me red-handed. I was trying to hide that. So here's another one. This is the last one for demos for today. So another quiz for the audience. What's wrong with this code? All right, now I've initialized it. Very good. Yep. When I initialize it to 1 and I add, I have a test where I'm testing the boundary condition for max. Therefore, when I add, it should do a signed overflow, which is undefined. And for a very good reason. And again, go watch that presentation from Chandler and he'll explain why. So as you can see here, it found this as well, saying, hey, you've just overflowed an integer. So if you're familiar with AUTOSAR and MISRA and safety critical system code and all of that stuff, this is a big deal, right? Because there's a ton of work that goes into trying to figure out, have I overflowed an integer just when writing safety critical code? Essentially every single addition, subtraction, multiplication, division, mod, all of that stuff, every single time you use one of those operators, you have to check for overflow. Total pain, right? But this can tell you right off the bat, hey, look, you're overflowing this integer over here in this test case. This is substantially better. All right, so back to the presentation. Yeah, an example of one where the error is not very good is if you were to overrun the bounds of an array. That's a good example of one where it's just going to tell you I couldn't do it. It's not going to let it through. It's just not going to be very helpful, and you'll have to sit there and figure it out. With the unit test that we have, which I'll show you like a real-world looking unit test, we have the ability to say, like, I want to run this specific test at runtime only. And then you can then run it at runtime, watch it, do whatever horrible thing it does, and then you can try and track it down from there. If you try to track it down from the compiler at compile time point of view, it's a pain.
So basically, you're saying that indirectly by asking that, you know, he knows you're running at runtime, he knows by asking that whether it's running without error, if that's like an entry level value of
So the question is, you know, could you end up in a situation where you never run into that particular compile time issue? Yes and no. Depends on how good your unit tests are. So again, the idea is you have to test all inputs. You can't do that, but in practice what we try to do is ensure that we test at least all the boundaries. So anywhere where the code's going to branch, anywhere where, you know, weird type of behavior like int max and min, you know, where weird things are going to happen, those are what we're trying to test. So as long as you do all of that, then you should technically, and as long as you have good coverage, you should be able to detect those issues.
Does the standard require that compilers make diagnostics for DB, or is it just strongly recommend that compilers?
The specification states that at compile time, undefined behavior shall not be executed. It does not state how pretty it has to be when it comes out. Yeah. So, question? So the question is this finding things that valgrind or maybe say the sanitizers, you know, couldn't find? The answer is yes. The sanitizers and even valgrind, they put hooks into the code to try and detect a lot of this stuff. Now, they do a really good job. And in the absence of being able to do this, that is hands down the best approach. And in reality, for 99% of the people writing C++, that is your best solution right now, is something like the sanitizers or valgrind. If you happen to be fortunate enough to be in a situation where you can do this, this is going to be more comprehensive. Yes. So the question was, is the microkernel from scratch like you write in 20? And the answer is yes. We'll get into that. Quite the effort. So that's it. You just have to, you know, write all your unit tests as a const expression, do it at compile time, and you're done, right? Just kidding. All right, so here's the problem. To get to your point, so thanks for the lead-in. In practice, this is extremely complicated because not all code can be run in a const expression. For one, you can't use global variables. And this has nothing to do with undefined behavior, mind you, right? There's nothing undefined about using a global variable. I think a lot of people would like it to be, but that's not true. Well, we know, like, for example, if you use to Rust, you have to actually declare it unsafe if you do it. So, and then there's no support for casting void star. This is going to creep up at the end of this. This is not cool. I'll explain why in a little bit. There's I think, an improvement that C++ can make here. There's also really any forms of type erasure that you can do. So things like, for example, std function aren't going to work at all. And I tried. I tried real hard. Most of the standard library in general is not const expression friendly yet. So there's been a lot of work, like for example in 20 they added support for string and for vector, if I'm correct. But there's, I mean, easily 90% of this thing still needs to be ported to C++ const expression support. So the question is something like the math library example something that's not Constexpr friendly? And the answer is there's a whole bunch of stuff. So like most data structures aren't right now. I mean, yeah, the most memory, stuff. Even like something which I thought was very odd, unique pointer still isn't Constexpr friendly. So there's a fair amount of the library that still needs to be updated to support this. So that kind of gets us into the BAREFLANK support library. So if you're familiar with my work, I've been working on the BAREFLANK Hypervisor for like 7 years. And the BAREFLANK support library was sort of step one into getting all this to work. We traditionally were using lib C++, which was fantastic. But we ran into issues, a number of them, and especially around sort of trying to get the hypervisor work into their architectures. If you don't happen to be running in, say, like a well-supported operating system, C++ can be a real pain. And so what we did was we started working on our own implementation of a C++ library that was designed to kill a whole bunch of birds with one stone. And the Constexpr aspect, part of it was actually not our driving factor. We didn't even know it was going to be a thing until we started working on it and realized that we could do it. And really the driving reason for starting the support library was because we could no longer support exceptions. And right now, the standard library is very dependent on that. If you turn exceptions off, you're kind of just burying your head in the sand. So we wanted it to be AUTOSAR compliant. So one of the craziest rules in AUTOSAR is that your standard library has to be compliant. I don't know if any that exists. I don't know how anybody actually follows that rule. But we said, all right, well, since we have to write this from scratch, we might as well make sure we adhere to that. We wanted to hit good testing, including MCDC, so you could use it for like, cars and stuff like that. So that's kind of how we started. And as we were developing it, we realized that this was a thing that we could actually strive for, and then it became sort of like this personal challenge, like how far could I possibly take this? And the answer was all of it. We did every bit of it. So we then used the support library to implement the BAREFLANK hypervisor. And that too went through a massive rework, and there was a whole bunch of stuff that we were trying to do with it outside of just Constexpr stuff. Things like adding native Windows support and better support for AMD and ARM and all sorts of stuff. It was a big, massive, 3-year-long comprehensive rewrite of the hypervisor. And so part of it was, instead of using a monolithic approach, we wrote a microkernel approach. And so we divided the hypervisor itself into 2 components, the microkernel, which is this tiny little thing that's designed to do policy enforcement, and then your extension, which is the actual VMM. It's the thing that actually implements the hypervisor. And so we're going to talk today about the microkernel, and we're not going to go into too much hypervisor stuff. Just know that it is a real microkernel. The only thing compared to other microkernels you might be familiar with is it doesn't have a scheduler, because it doesn't need one. But it does all the same things. It has, exception, handlers, and it does interrupt handling, and it, loads ELF files and runs them. It does memory management with page tables and allocators and all the things that you see in kernels today, it does. AIS today is actually using this architecture to build a type 1 implementation of KVM. So something that can run like KVM on Windows instead of Linux, for example. So they're currently in the process of building this. And so the part we're talking about is just that little box at the bottom called the BAREFLANK microkernel. Everything else above is the actual hypervisor, and that's all the stuff that's out of the scope today, although the micro V extension is being written the same way. So it is also going to be all Constexpr, unit tested and critical system compliant, written with the BSL, all of that. Yeah, so the whole point of the new architecture was that we had a lot of people who wanted to run user space software inside of BAREFLANK, for example, for doing reverse engineering with libvmi. And doing all the cross-compilation and stuff was a pain because there's different languages that are used. We also had people who wanted to run or write their VMM in Rust and not in C++. And so to support that sort of flexibility, we used the microkernel approach because it allowed anybody to write the VMM in whatever they wanted. It's just an ELF file that we load. It's a normal user space app, and you just kind of do what you want. So yeah, I mean, it's a real microkernel. So I mean, really, the point of all of this is to kind of demonstrate that we're talking about a real world application here. This is not a simple hello world or some fancy exercise like we just went through. This is real code that's actually used. The hypervisor right now is 100% unit tested. It is being used, and it works. And so we were able to take a very complicated piece of code and write it as a const expression with C++20. But yes, we did have to write everything, all of its dependencies, from scratch. There are some exceptions. Okay, so I say almost 100%. Virtual to physical address conversions or translations still require reinterpret cast. So I don't have a way of doing that. That should stay that way, frankly. There's no reason to fix this. This is something that should stay the way it is. It should not be allowed. The way we handle it is safe. It's the same way everybody else handles it. But from a const expression point of view, there's no reason to fix this, and I'll show why in a little bit. It's a very isolated little piece of code you don't have to worry about. C in assembly is also only tested at runtime for obvious reasons. The main function itself, which is what stores all the global variables, that too is also tested at runtime. Reason being is you can't use global variables in a const expression, or at least you're not supposed to. There's hacks. So what we do is the main function does nothing more than calls the microkernel main, which is the actual main function. And all it does is it takes all the global variables and passes them as parameters to that function. So yes, there is a main function that takes 11 parameters inside the microkernel. And it's so that we can pass every single global variable as a parameter to the rest of the code, and then the rest of that code is all now const expression friendly. And it all passes everything through parameters. If you're familiar with the art of unit testing, they talk about this thing called a seam. That is one way to do it. That's how we chose to do it. So yeah, even though the main function is tested at runtime, it doesn't do anything. It just runs the actual main code by passing global variables as parameters.
Just to highlight, just before the dissociation, his motivation for context expression was basically to get away from the binary side and very short execution time. So I just have a question, that your main motivation is just to leave that as ABB rather than actually running anything at the compile time?
So our main motivation when we started, so the question is the motivation for using Constexpr because of optimizations, or is it because of undefined behavior? And so to start, it was optimizations. So again, we didn't start off going, oh, hey, we can do this to detect undefined behavior. That sort of emerged as we were doing development. The whole reason for doing everything as Constexpr was for optimizations. And what a difference. The size of the microkernel is 105 kilobytes, and I really tried hard to get that to 99 just for the heck of it. But it used to be almost a megabyte in our previous versions. So it was a massive reduction in size. Now, part of that was getting rid of libc++. But honestly, libc++ itself is also header only mostly, and with LTO, you can get rid of most of that stuff with optimization as well. The code as a Constexpr can be crazy optimized to a point where it actually became a problem because in some cases it will assume an infinitely long stack and it'll just start loading the stack up like mad, and since we're in a limited resource environment, that's a problem. And so we had to take some schemes to get the Constexpr code to stop doing that. It'd be great if the compilers offered a flag that said, no more than this, please. So it started off as optimizations. That's why everybody should do Constexpr. This is, if you have the ability to do this, great, but Constexpr really, flexibility, optimizations first. What came from it, though, was as we were rewriting everything from scratch, was we realized that everything was working as a Constexpr, and we were able to do our unit tests at compile time, and we just kept going. So we're going to go through, to kind of conclude this, we're going to go through a real world example of where this gets quite complicated. So we're going to build a page allocator. All right, so this page allocator is going to allocate a page being 4,096 bytes, and it's going to return it as a type T star. We can then deallocate that page, and we'll be able to do something called vert to fizz and fizz to vert translations. So that's just a fancy way of saying, I give you the address, that T star, you give me some random integer, right? You give me that random integer back, I can give you that T star back. Okay, that's how we're going to view that for now. We're going to build this as a simple linked list. So we've got our, the head of our linked list, and then we've got this thing called a node T. That node T has the next node, and then all it does is it has a buffer that's 4,092 bytes on 32-bit, right? Or whatever for 8-bit, or 64-bit rather. So it's just a buffer of a bunch of bytes that is taking up the rest of that page. And then we just link until we hit the end. So this is pretty simple. I want to allocate memory. All I have to do is pop the node T from my linked list. I'm going to tell it you're no longer a node T by destroying it. And I'm going to say now you're a T star by constructing it and returning the new T star. So if you're familiar with construct at and destroy at from C++ 20, or at least ones from 20, I can't remember when destroy at was added, but that's how you use them. To deallocate, we just do the reverse. We say, okay, you're no longer a T star, now you are a node T, and then we push it back onto the linked list. Really simple. And there was one assumption at the very bottom of that page right there. I assume T is a POD type. Now you actually don't need it to be a POD type to do this. You can, I think it's just trivially copyable is all you need. But since everything that we're doing is POD, it was fine. POD was, you can be sure that it's no issues if it's POD. All right, so vert to fizz. Really simple. Again, all we were saying is that I take in a virtual address and I want to give you some random integer value. So in this case, what we're going to do that is we're going to turn our T star into an integer using a reinterpret cast, and I'm going to subtract some sort of offset. The question is, can we use a bit cast? I don't know the answer to that question. Yeah. Correct. I don't think you can do bit cast with a pointer to integer at all. I have to look at it, but I'm pretty sure there's a rule that says you can't bit cast a pointer type. Yeah, something like that. I'm pretty sure the standard says you can't do that. So, for Constexpr, definitely, because Constexpr doesn't have a pointer value to do this with. So that's the big issue with Constexpr. There is no address for the pointer. It's just an AST, so it doesn't have that. If you're familiar with OS Dev, you'll know that this is a direct map implementation. So the reverse for fizz to vert is you take the physical address, you just add the offset, and you do the opposite. We cast back. And that is quite literally the code that you need for this. Now, assuming that all of your pages are in your direct map and you're doing that right. I don't want to go into the details of how that works. Just, if you're interested, go look up, direct maps on OS Dev and you'll learn all about it. The important thing to understand here is that so long as the memory was allocated from my page allocator, then I can do vert to fizz and fizz to vert this way very safely. It is definitely not Constexpr friendly though. So how do we unit test this allocator? Well, first off, the vert to fizz and fizz to vert can't be done in a Constexpr, plain and simple, and there's no reason to fix that. Again, it's one line of code per operation that I need, and there's a nice simple way to deal with this for the rest of my code. So leave it that way. That code I test at runtime, and all I have to do now is ensure that I'm following some simple rules. First off, T needs to be something that I can, to do that type of conversion with. And I need to make sure that I do follow the rule that I'm only ever doing vert to fizz and fizz to vert for things that I'm allowed to do that for. So as long as I can adhere to those rules, then I can safely allow that code to only ever run at runtime, and there's no big deal here. So that's what we're going to spend the next part of this going over. The rest of it, allocate and deallocate, can be done from a Constexpr. There is one problem, though. I talked about earlier, you can't change the type of a variable in a Constexpr. So I did the destroy and construct that, but if you were to run that inside of a Constexpr, it's going to yell at you saying, hey, this was a node T, and now you're trying to give me a page T. You can't do that. It's a node T. And so, but it's like, yeah, but I just destroyed it, construct, and it's like, no, you can't do that. Unless you're a union. If you're a union, you can do that. But then I'd have to know every single type that I want in my actual code, and that would be a pain. And of course, unions can't be used in AUTOSAR, so you're kind of screwed there too. So the issue is that I need some way to be able to unit test this, but I can't really test the different types of T. So what we're going to do is we're just going to, in our unit test for this code, we're going to unit test allocating node Ts. That was what made up the linked list, so I can allocate a node T and then put it back and never changing the type, but I can fully exercise all of the code. So the only code that's not being exercised is the ability to change its type from one type to another. So you better make sure you get that part right. But as long as you do, you're good. So that's how we unit test the real page allocator. We do vert to fizz at runtime because we don't have a choice. And at compile time, we can do allocate, deallocate without a problem. We just have to make sure we're not changing T. All right, but we still have a problem. We just said that we can't do vert to fizz and fizz to vert in a const expression, and we can't change type T with allocate and deallocate from a const expression using our allocator. Well, okay, the rest of the code, though, it's going to have to allocate different type T. I mean, not everything can be a node T. And I'm going to have to be able to do vert to fizz because I'm going to create page table logic and stuff like that where I'm going to have a physical address and need to get my virtual address and back and forth. And what am I going to do? So we have to come up with some sort of solution to this, and that's where mocks come into play. So a mock is nothing more than just a subcomponent that behaves like another subcomponent so that I can test another subcomponent. So in this case, I'm going to create a mocked version of my page allocator. And mocks normally contain simpler logic than what you would have in your actual code. But in this case, it's wildly not even close, right? The mocked version of the page allocators you'll see is substantially more complicated. But we do it so that we can do everything from this, this const expression and fully unit test everything I've got. It also does require seam. So going and taking, some 10-year-old project that's got, a million lines of code and doesn't have a single seam anywhere is going to be really hard to unit test with mocks without, potentially having to rewrite large portions of code. And so, and again, if this language doesn't make much sense, I highly encourage you to go read The Art of Unit Testing. It's a fantastic book. It's in C#. I think most people can handle that. It's, but all of the rules apply for C++. It's fantastic. And it's definitely something everybody should go look at. All right, so to create our mocked version of our page allocator, we're going to, well, we started with the real one, right? So we pop, we destroy, and we construct. In the new one, we're going to allocate a new T star. We can do this thanks to C++20, where we can allocate and deallocate memory from a const expression. So long as all memory allocated is deallocated before the Constexpr finishes. But this is great, right? Because now my const expression is not just going to tell me if I'm doing, executing undefined behavior. It's also going to tell me if I've leaked memory, which is awesome. Then from there, I have to create some sort of physical address. Again, I don't care what the physical address is. It just has to be unique. And so I'm just going to create, because we're dealing with 64-bit here, but even 32-bit this would work. I can, add a page over and over and over all day long in my unit tests and just create this ever incrementing number that just increments by 4096 every time I create a new allocation. So that's an easy one to solve. So then finally, I need to deal with vert to fizz and fizz to vert. So what I'm going to do is I'm going to store my physical address in a map given a virtual address, and I'll do the reverse. I'll store a virtual address given a physical address in a map. Of course, since C++ doesn't have a map today that supports Constexpr, we had to rewrite that too. And then finally, I return the vert. Deallocate, well, this is not exactly the opposite. This is going to first check to see if my map contains the virtual address I'm trying to deallocate. This enforces the rule that you can only deallocate memory you've allocated with the allocator, which is awesome, right? Because now all my unit tests can prove that, hey, I have ensured that you're never giving me some address I've never seen before. Right? You haven't moved it and somehow you haven't given me like, some address to an array somewhere inside the array. You haven't given me a null pointer or something like that. Then the rest of it's in the reverse, right? I get my physical address from my map, I then delete, and then I erase, all evidence that this ever took place. Okay, so now vert to fizz and fizz to vert, these are easy, right? No big deal. I need to return the virtual address I need to return the physical address given a virtual address, and so I just look it up in the map, right? Easy enough. Same thing for fizz to vert, right? No big deal. I just do the opposite. Well, except for the fact that I'm returning a T star. How do I store that T star? Right, so everything else up to this point was easy. This one, not so easy. Because I can't just store a T star. I don't know what T is. T can be anything. So normally what we would do is we'd store a void star. But you can't upcast from a void star to a T star in a const expression. So how do I get from, I can't do type erasure. So how do I get from a void star to a T star? Well, the answer is there's no way to do this easily. So we did it this way. In our unit test, we have a helper function that you can define yourself if you're going to use this code. And you tell it every single type of T star that you're ever going to allocate, and you reserve space in the struct, and then using compile time logic, it determines what type you were given, and then figures out what pointer it needs to store, and then it can return the T star as a result. Now, you could do this with a union as well, right? But then the code that actually does allocation would have the union. And AUTOSAR is not going to be happy with you if you do. So this takes up a lot more memory by doing it with a struct, but you get to the same result and everybody's happy. So this allows me to store, without using type erasure, the T star pointers for everything I need. This should not be necessary, right? The compiler should be keeping track of this for me, not me, right? I shouldn't have to create a giant list of every possible pointer type, just so that I allocate as type T, go to void star, and then go back to the exact same type T I started with. I'm not doing anything wrong, right? But for whatever reason, right now in the spec, that's not allowed. So that's the thing that needs to be fixed, so that this is never needed. And then from there, you could just store your void star. You could then cast to the type that you care about, and the const expression would look at you and say, oh, you allocated me as a page table, and now you're trying to do a TCP block, and you can't do that. You change the type, right? That shouldn't be allowed. But what should be allowed is to me to go from a page table to a void star back to a page table. And so the const expression logic could actually assist in determining whether or not you're changing types when you're not supposed to. So this was the last hack that was really necessary to pull all of this together. And we ran into this a number of times. Essentially, any single time you had to do type erasure like this was the solution that we employed, was create some giant struct and do it in a way where I could easily override it and change it, because some of the code that's in there is meant to be used by not just the microkernel, but by other people writing their extensions, and so they'll need to add their own types to this, and so we had to plumb in seams to be able to do that. But in general, this worked really well. All right, so final thoughts before we take questions. So big thing is, and I posted some of this stuff up on Reddit, and I kind of get some feedback to see what people thought. And of course, it always inevitably ends up causing this, oh, you should be doing this in Rust, and I can't believe you guys are doing this in C++. You're killing mankind by doing that. There's always some horrible, it always devolves into something terrible. The reality is you can write safe C++ without any other tools. This was all done with just a C++ compiler. And I can determine that no undefined behavior ever executes by doing it. Or at least for all inputs that I've given my unit tests. And again, no, I can't do all inputs, but I can get really close, right? Practically speaking, I'm getting close enough. So yes, you can write, safe C++. There is, one of the questions that always comes up is, can I do this with existing logic? And the answer is yes. So long as you can compile it in a const expression. So you don't need to rewrite everything. You won't be able to test everything in a const expression unless you do that. Or we get to a point where the standard library and everybody else is playing nice in this space. But for new code that you're writing that doesn't rely too heavily on that stuff, if you can, you should. Right? If you're writing a function and it doesn't have dependencies that won't work in a const expression, all you have to do is take that function that you're using as your test and just run it in a static assert and you're done. It's that simple, right? So if you have code that can do it, just do it. Finally, the last thing is that I personally believe that this should be part of AUTOSAR MISRA, right? It does a much better job at helping to identify some of these issues. And if you're driving in a car and it's controlling your braking system, I personally would love to see that code having gone through this rigor instead of, not at all. So that's all I have. If you don't believe this, by the way, all that code's up on open source. You can go and look at it and see that it is in fact a microkernel and it does in fact execute all of its code inside a const expression. Questions?
Okay, this is more related to Microkernel and the hypervisor. So on the hypervisor side, this interactive networking protocols, network libraries like etc.
The microkernel itself is a traditional microkernel. It does not have device drivers or anything like that. Now you could add, to your extension that kind of code if you wanted to, but we certainly don't add that. Question? Yeah, so fantastic question. So the question is to what extent do we test for reentrancy? Quite a bit. That is actually an area where you're not going to do that from a const expression. You'll try and do that using regular threading or whatever you can to test for all that. But that's okay, right? As long as all of the code is unit tested from a const expression, then you can do all these other sort of tests you want, not in a const expression that tests other things that wouldn't be looking for undefined behavior. So you have like one set of tests that's all my undefined behavior tests that does 100% code coverage. And then from there I do reentry seed tests or deadlock tests and all sorts of other stuff that you can do. So quite a bit. With hypervisor logic and the fact that it's very symmetric kernel, we don't want to be polluting the TLB. So there's a ton of work in there ensuring that the code almost never crosses between any issues like that. So it's very single threaded on a per core basis, and then they never really touch each other ever. Let me get a question back here. I haven't. There's nothing that would prevent you from doing it. What I will say is that in the boundary conditions that we were testing, where we, again, you first start with the obvious, get to 100% code coverage, and then from there you test all the scenarios that you can think of, that are above and beyond all of that. Some of that code can take 10 minutes to compile, because you've got a unit test that might be tens of thousands of lines. And you might ask, well, why not break that up into separate unit tests so that you can do them in parallel at least? Well, the unfortunate situation in open source right now is that if you're using C++ and you're dealing with templates, then all the code coverage tools get very mad at you very quickly when it comes to branch coverage. And so the way to solve that is all of the code for that particular, all the tests rather for that particular piece of code need to be contained in a single executable. Otherwise, it will basically say that you haven't tested something when you have many times. So you end up with this code that's just massive and it's all being compiled from Constexpr. So there's strategies around that. You could break it up for the Constexpr part and then not for the runtime part for your code coverage. There's lots of things you can do, but the reality is that you want to be mindful of the fact that the compilation time is going to be pretty high. And so fuzzing already takes forever. Doing that from the compiler is going to take even longer because it's not executing at the speed at which it would on the system. It's having to traverse an AST, and that's horrible. So good idea, definitely worth doing. Nothing preventing you from doing it. Just be mindful that it might be sitting there for a couple years. I don't have on the top of my, so the question is, are there any examples that UBSAN isn't collecting that you could do with this? I don't have anything off the top of my head. I did have a couple for when we first started, but unfortunately I don't have memorized. There are some, but yeah, absolutely. Again, like I said before, the right answer is most people should be using UBSAN to detect most of this stuff. That's what you're going to be able to apply to your tools right now. And you still need good code coverage for it to work. Fuzzing libraries can help too. But if you can do it this way, it is more comprehensive because it's having to quite literally traverse through the compiler, and the compiler is going to know very quickly that, hey, I just hit a case that I know is undefined. Versus on UBSAN, it's having to hook the code and try to make those determinations as it's executing through those hooks. And that's it's a lot harder to do than it is from the compiler's point of view. Trying to be even here. So actually behind you. No. So the question is, did I ever try to get the code coverage tools to work at compile time? And did I ever run into issues with the fact that one was compile and one was runtime? So interestingly enough, as long as it ever compiled at compile time, it always succeeded at runtime. Because again, you're taking the unit test function, you're executing it in a static assert, and then right away, you're just executing it and saying pass or fail for runtime. So the two are almost identical. The reason you can't do code coverage at compile time is the code coverage tools are outputting files to the disk that contain all the coverage reports that you can't do at compile time. So you need that runtime component to do that. There absolutely could be a difference between the two if there happens to be some sort of bug or issue within Clang that's not being picked up. So always take everything with a giant grain of salt and always run everything. Like in the CI environment that we have for all this stuff, we still run UBSAN and ASAN. It never found anything, but we still run it. I just it's like it gets that little warm and fuzzy that it was all working right. So yeah, I hope that answered your question. Okay, and I'm being told that I'm out of time. So if you have any more questions, please feel free to come up and ask, but thank you very much for your time.